Today we are living in the computer age. In fact, most of our economic lives are controlled by computers. Our bank accounts, credit cards, mortgage payments, even income taxes. Computers help us to calculate, store, and process facts and figures that are difficult for the human mind to handle and retain. The navigational flight computer is no exception to this. It's an indispensable tool for every pilot. The next two programs will concentrate on dead-reckoning flight computations using both a manual flight computer and an electronic flight computer calculator. This will focus on the manual computer. We'll demonstrate the E6B type most commonly used by students and private pilots. And the second program will demonstrate the use of the electronic flight calculator, which an increasing number of pilots are utilizing in their dead-reckoning navigation. This is the E6B style of manual computer. Let's get acquainted with its basic components. These components are the computer face, the wind face, and the sliding grid. We'll be using the computer face for our first problems, so let's examine its various features. These two arrows convert nautical miles to statute miles or statute miles to nautical miles. They also convert knots to miles per hour or miles per hour to knots. Later in this lesson, we'll be utilizing these airspeed and density altitude computation windows to set up altitudes necessary to work true airspeed and density altitude problems. Most frequently used in dead-reckoning navigation will be the A, B, and C scales. These scales are necessary because the computer is actually a circular slide rule. It features special indexes used to solve simple ratio problems. The outer, or A scale, is fixed. The B scale is movable. The C scale moves when the B scale is moved. C is fixed in relationship to the B scale. The three scales are used to solve these dead-reckoning problems. Time and distance problems, in which the aircraft speed is also a factor. Fuel consumption problems, in which we determine the rate at which fuel is consumed, or the total fuel flow in a specified time, or the time we can fly on a specified quantity of fuel. Conversions using the previously pointed out arrows on the outer or A scale. We can also multiply and divide on the manual computer, although this function has been made virtually obsolete by the availability of inexpensive electronic calculators. Time and distance problems and fuel consumption problems involve a fundamental relationship between rate or speed and the time required to fly a specific distance at that speed. The relationship is expressed by this formula: R equals D over T. R is the rate of fuel consumption, or the rate or speed of the aircraft. D is the distance flown, and T is the time required either to consume fuel or to fly a distance. The formula can be rearranged to solve for problems in which any of these two factors are known and the other is unknown. By adjusting the computer's A and B scales, any of the combinations of knowns and unknowns can be set up to solve the problems. The ratio is always like this. The rate arrow always represents 1 hour, and thus is one of the knowns. For example, you know distance, 25 nautical miles, and time, 15 minutes. Ground speed is the unknown. Read it over the rate arrow, 100 knots. Substitute an unknown in any of the positions, and if you know the other two, the problem is solved. Depending on the problem you are solving, the A scale may represent nautical or statute miles of distance, knots or miles per hour speed, gallons of fuel consumed, or true airspeed. The A scale also features the number 10 enclosed in a distinctive box. This is to remind you that the index marks the beginning of the scale of numbers. In using the computer, we must use a procedure known as assigning number values. If we align the 10 indexes on the A scale and on the B scale, you'll see that both scales are numbered in the same way, and that there is no 0 on either scale. The 10 can stand for any combination of zeros and ones we need in any problem. Let's work a conversion problem to illustrate the concept of changing number values. Assume we wish to convert the speed of 130 knots to a speed in miles per hour, but nowhere on the scale of the computer is there a 130. Thus, we must assign a number value of 130 to 13. Logically, if 13 becomes 130 in our problem, then we must assign a value of 120 to 12 and 140 to 14. We then set 130 under the marked naught and read the answer under the arrow labeled stat for statute miles or miles per hour. The 15 has a number value of 150 miles per hour. Dependent upon the values in the problem we are working, any of many number values can be assigned to the numbers on the computer scales. For example, 13 could have a number value of 0.013, or 1.3, or 130, as we have just demonstrated, or 1300, or 13,000. However, the problems we shall be working involve relatively low speed and low fuel consumption airplanes. The number values assigned most often would be 1.3, 13, or 130, as you will see shortly. We also need to observe the scale increments before we work further problems. Note graduated units decrease in size as the numbers increase in size. Between the numbers of 10 and 11 on the A and B scales, the unit is divided into 10 smaller divisions. Refer to the numbers 15 and 16, and you'll see that the interval is now in values of 2. There are no numbers shown between 25 and 30, yet it's obvious that the larger tick marks are 26, 27, 28, and 29. The intervals between 30 and 35 have large tick marks equaling increases of 1, or 31, 32, 33, and 34, with the shorter tick marks in values of 5. The secret to successfully using the E6B is assigning the correct values to the many tick marks between the numbers on the computer face. With a little practice, you'll be able to make the correct assignment of values to these marks. A vitally important feature of the B scale is the rate arrow, also called the speed index. Note that it is aligned with 60 on the B scale. It represents 60 minutes per hour. In time and distance problems, the rate arrow will be set opposite the speed of the airplane. Let's examine the C scale. This scale converts minutes to hours to aid your computations. Note the hours and minutes are written out in 10-minute increments from the rate arrow to 2 hours. Then in 30 minutes from that point to 5 hours. And in 1 hour increments from there back to the rate arrow. The ticks are in 5-minute increments from the rate arrow to 2 hours, and are in 10-minute increments from there back to the rate arrow. "120 minutes is thus 2 hours. 150 minutes is 2 hours 30 minutes. The tick marks between would thus be 2 hours 10 minutes and 2 hours 20 minutes. Conversely, if we wish to convert hours to minutes, 7 hours is 420 minutes. 7 hours 10 minutes is 430 minutes. 7 hours 20 minutes is 440 minutes. And 7 hours 30 minutes is 450 minutes. The problem which students have in working computer problems initially is in assigning the correct number values to answers. So we suggest in working any problem that you arrive at a common sense approximation of the answer before you decide on the number to assign the computer. Let's look at an example. We have flown 21 nautical miles in 12 minutes. What is the rate of speed? A guesstimate reveals that if we fly 24 nautical miles in 12 minutes, the speed would be 2 nautical miles per minute. Since we were slightly under 24 miles, our speed is somewhere just under 120 knots. Now let's solve this problem. First, set 21 nautical miles on the A scale over 12 minutes on the B scale. Using the rate arrow located on the B scale, read the answer 105 on the A scale. Our speed is 105 knots. By making a guesstimate first, we avoided a gross error of assigning an incorrect number value to the number 10. Instead, 10 became 100 and 11 became 110. The 10 increments in between now each have a value of 1. The rate arrow points to the answer of 105. Assume now that we continue flying at the ground speed of 105 knots. How far can we fly in 40 minutes? No, don't touch scale B because the rate arrow must remain on 105, our ground speed. Locate 40 on the B scale. Above 40 we find the figure 70 on the A scale. But what number value do we assign to 70? Is it 7, 70, or 700? Well, we flew for 40 minutes, thirds of an hour, at 105 knots. So once again, a guesstimate tells us that 2/3 of 100 is close to 66. So our number assigned is 70, not 7, and not 700. Let's try another one. The distance flown is 37 miles in 17 minutes. What is the ground speed? First, locate 37 nautical miles on the A scale. Place 17 minutes below it on the B scale. Find the rate arrow on the B scale, and above it read the answer 130 knots. In this next problem, let's solve for time to fly a certain distance at a given ground speed. In our pre-flight planning, we have estimated that our ground speed will be 98 knots on a flight of 312 nautical miles. How long will it fly this trip? When speed is one of the two knowns, we first set the rate arrow opposite that speed of 98 knots. Remind yourself again, miles are on the A scale, minutes are on scale B. We are flying close to 300 miles at almost 100 knots, so common sense tells us that the flight will require about 3 hours to make. Now to set up the ground speed of 98. There are 10 increments between 90 and 100, so we readily locate 98 and set the rate arrow opposite it. We now locate 30 on scale A, which we must assign a value of 300. Each of the longer tick marks has a value of 10. There is no tick mark to indicate 12, so we'll approximate its position. We previously approximated an answer of 3 hours for the flight. By reference to the hours scale, we find 180 minutes equals 3 hours, while 191 minutes would be our answer of 3 hours 11 minutes. Let's solve another time problem. Given a ground speed of 115 knots, how long would it take to fly 25 miles? Locate 115 on the A scale, then set the rate arrow below it. Locate 25 on the A scale, and read 13.1 minutes on the B scale. Round this off to 13 minutes. For practice, let's do one more. Ground speed is 125 knots. The distance flown is 320 nautical miles. How long will this flight take? Place the rate arrow below 125 on the A scale. Locate 32 on the A scale. Read below on the B scale 153 minutes. Continue down to the C scale to read 2 hours, 33 minutes. When you have mastered time and distance problems, Fuel consumption problems can be completed with comparative ease. These are set up in the same way as time and distance problems, except that numbers set opposite the rate arrow will indicate gallons per hour, and total fuel burned will be read on the A scale, while time will again be located on scale B. Note that we compute fuel consumption in gallons per hour consumed, rather than in miles per gallon as in automobiles. Assume your airplane consumes fuel at the rate of 11.2 gallons per hour at the altitude and power setting selected for a flight. You estimate in your pre-flight planning that the flight will require 4 hours 32 minutes to make. Our common sense estimate would tell us that 4.5 hours at 11 gallons per hour would equal 49 gallons. Since gallons per hour is known, we first set the rate arrow opposite 11.2. Then locate 4 hours 30 minutes on the hours scale. 4 hours 30 minutes is opposite 27 on scale B. Increments between 25 and 30 have a value of 2. We count one increment to the right for 272 minutes, or 4 hours 32 minutes. Directly opposite that number, we read the total fuel required on the A scale. The answer can be rounded out to the nearest value of 50.8 gallons required for the flight. Here's another problem to determine the fuel required for a flight. The fuel consumption is 9.6 gallons per hour, and the flight time is 4 hours and 20 minutes. How much fuel will we need for this flight? Set the rate arrow under 9.6 on the A scale. Locate 4 hours 20 minutes on the C scale. Read 41.8 gallons on the A scale. This flight requires 41.8 gallons. Here's a fuel consumption problem with different knowns. We topped or filled the skipper's tanks at the completion of a flight. The fuel receipt shows we consumed 12.4 gallons. Our flight log indicates a flight of 2 hours 12 minutes. What is our fuel consumption per hour? Simple arithmetic reveals the assignment of numbers in the problem. We'll have close to 6 gallons per hour. Since total fuel and time are known, we locate 2 hours on scale C. The tick marks between 2 hours and 2 hours 30 minutes have a value of 10 minutes each. Above 2 hours 10 minutes, we find 13 on the B scale, which equals 130 minutes for this problem. 2 increments to the right, we locate 132 minutes, or 2 hours 12 minutes on the C scale. Next, rotate the B scale to set 132 opposite 12.4 on the A scale. Note the 10 increments between 12 and 13. Now locate the rate arrow. The arrow points between 55 and 60, but since we have already estimated an approximate 6 gallons per hour consumption, assigning number here has been determined. 55 will have a value of 5.5. The longer tick marks each have a value of 1. Fuel consumption is 5.63 gallons per hour. Let's do one more rate of consumption problem. We topped our tanks at the close of our flight with 24 gallons. Our flight was 3 hours, 40 minutes. What is the hourly consumption of fuel? Locate 3 hours, 40 minutes on the C scale. Set this below 24 gallons on the A scale. Find the rate arrow and read outward on the A scale the rate of 6.5 gallons per hour. Let's compute how long a Beach Bonanza equipped with 80-gallon fuel tanks containing 74 gallons of usable fuel can remain in flight. We select a power setting of 11 gallons per hour. To simplify the assigning of number values, we make an estimate that 74 divided by an approximate 12 gallons per hour will yield an endurance of about 6 hours. When a per hour value is known, as 11.8 gallons per hour is known in this problem, The rate arrow is always set first. Then we locate 74 gallons, the usable fuel available on the A scale. Read on the C scale the time of 6 hours and slightly less than 20 minutes, or measuring carefully 6 hours, 18 minutes. Let's work another endurance problem. The fuel consumption is 7.5 gallons per hour. Usable fuel available is 37 gallons. How long can you fly? First, set the rate arrow opposite 7.5 on the A scale. Locate 37 gallons on the A scale and read down on the C scale 4 hours, 52 minutes. Remember, though, that this is endurance without reserve fuel. By regulation, we are required to have 30 minutes reserve fuel for VFR flight during the day and 45 minutes reserve fuel for VFR night. Consider this required reserve a minimum. Another feature of the computer is the capability to calculate true airspeed, the actual speed the airplane is moving in reference to the air around it. True airspeed is a vital factor in your flight planning. Let's figure an in-flight true airspeed problem. You remember from your study of aircraft instruments that the airspeed indicator responds to air density. Thus, indicated airspeed, as read from the indicator, may differ considerably from airspeed, dependent upon temperature and altitude. Let's take a look at the computer feature which computes true airspeed, and work a typical problem as we do so. We'll be setting the temperature in Celsius opposite our pressure altitude in thousands of feet. Then we'll locate calibrated airspeed on scale B and read true airspeed opposite that on scale A. To read pressure altitude on the altimeter, we must set it to 2992. The altitude of 1900 feet, which we then read, is pressure altitude. Next, we read the indicated airspeed. At cruising airspeeds, the indicated and the calibrated will probably be very close to each other, so much so that some pilots use indicated airspeed to compute true airspeed, but the E6B uses calibrated airspeed accuracy. So we use the pilot's operating handbook to find the airspeed correction table. We find that at our indicated airspeed of 70, the correction factor is -1 knot. Our calibrated airspeed is thus 69. We now have the three knowns necessary to work the problem. We set our outside air temperature of plus 25 degrees Celsius opposite 1900 feet pressure altitude in thousands of feet. Next, go to the B scale and locate 69, the calibrated airspeed. Then directly above calibrated airspeed, read the true airspeed 72 knots on the A scale. There are a couple of important precautions to take in setting up temperature and altitude. You'll note that temperature is given in plus degrees and in minus degrees. Be sure to select the correct side of and altitude is given in thousands of feet. So this is 5,000, 10,000, 15,000. You'll come up with some very erroneous answers should you read altitude in hundreds of feet. Let's work one more true airspeed problem. This one is a typical problem from the FAA private pilot written examination. Calibrated airspeed is 120 knots. Pressure altitude is 5,500 feet. The outside air temperature is plus 10 degrees Celsius. What is the true airspeed? First, we'll set plus 10 degrees Celsius over pressure altitude of 5,500 feet. Then locate 12 on the B scale. We assign it a number value of 120 in this problem. Opposite 120 on the B scale, we find the true airspeed 132 knots on the A scale. A vital computation from a safety standpoint is finding density altitude. If you need a review of density altitude and its effect upon aircraft performance, we suggest you refer to your text. Briefly summarized, high density altitude has an adverse effect upon aircraft performance. low density altitude has a favorable effect. The altitudes of airports where you plan to operate must be converted to density altitudes by applying non-standard temperatures which may exist. We compute density altitude initially using the same window on the computer in which we began true airspeed solutions. Assume we are planning a departure from Lake Tahoe Airport, where the pressure altitude is 6,000 feet, and the outside air temperature is plus 30 degrees Celsius. Set plus 30 degrees Celsius over 6,000 feet pressure altitude. Locate the answer 9,000 feet opposite the arrow labeled density altitude. The air at Lake Tahoe under these conditions is equivalent to the density of air at 9,000 feet under standard conditions. So far, we've covered the computer side of the E6B flight computer, solving problems for ground speed, time and distance, endurance, rate of consumption, and true airspeed, as well as density altitude. On the next program, we'll turn the computer over to the wind side and compute wind correction angle and ground speed. On our last program, we showed you how to compute time, distance, fuel consumption, and airspeed on the circular slide rule of your E6B computer. On this program, we'll turn the computer over and explore the wind face side, and learn to compute the effects the wind has on the airplane and the wind correction angle needed to maintain our course, which results in true heading and our ground speed. Introduce you to a small, lightweight electronic navigation computer which is designed to help you solve navigation problems in flight planning and execution. Now, let's look at the wind face. We have learned that an airplane flying in a crosswind will drift off course unless a correction is made by turning the airplane into the wind. The amount of correction between the true course and the direction the airplane is now pointed is called wind correction angle. We have also learned that an airplane flying into a headwind will have a ground speed which is slower than the true airspeed. An airplane which is flying with a tailwind will have a ground speed higher than the true airspeed. In flight, there will usually be some wind experienced. It may be a headwind from the right, a headwind from the left, a tailwind from the right, a tailwind from the left, a direct crosswind from the left, a direct crosswind from the right. Rarely will you experience a direct headwind or a direct tailwind. The effect of any of these winds upon aircraft ground speed and true heading will be solved on the wind side of the computer. Before we work a wind triangle problem, as these problems are called, we need to identify the components of the wind face. A rotating transparent disc contains a compass rose on its outer border. In the center of the disc is a reference circle called a grommet, which will be a starting point for certain calculations. At the top of the slide is a summary of steps in working the wind problems. Don't be reluctant to use this memory aid until you become proficient working the problems. The dark line down the center of the slide is aligned with the true index feature on the frame, which holds the rotating disc. The true index references all in the wind problems to true north. The vertical lines radiating from the bottom of the slide are the wind correction angle lines. Note that they are marked in 5 and 10 degree increments. The dark horizontal arcs, with 4 increments between each of the dark lines, are called the speed circles. They are numbered every 10 knots or miles per hour. The intermediate lines thus have a value of 2 each. It is on these lines we'll set up the speed of the wind and of the airplane. This scale, marked variation east and wind correction angle left, and variation west and wind correction angle right, is to assist you in arriving at the correct answer arithmetically. With this brief introduction and description of the parts on the E6B's wind face, let's work out an example problem given the following information. The winds aloft are forecast to be from 240 degrees at 26 knots. Winds aloft are stated in the true direction from which the wind is coming and in knots. Your true course has been measured in pre-flight planning. It is 195 degrees. The true airspeed will be 104 knots. We'll solve for ground speed, wind correction angle, and true heading. Step 1 on our memory aid tells us to place the wind direction under the true index. So we rotate the movable disc until 240 degrees is under the true index. Step 2 instructs us to mark the wind velocity up from center. We'll move the slide so the grommet is over 100. Actually, you can move the slide over any of the dark speed circles to count the wind speed up from the grommet, but beginning on 100, which now becomes 0, aids students in counting the correct wind value. Each dark circle is 10 knots, so there is 20. Each intermediate line has a value of 2, so we count up 2, 4, 6, and place a dot, or an X, so it is very visible over 26 knots, our wind velocity. The finish on the disc makes it easy to erase either soft pencil marks or washable ink from the surface as you continue to compute other problems. Step 3 tells us to place the true course under the true index, so we rotate the disc until 195 degrees is directly under the true index. This second rotation of the disc will be the last time we move it in working the problem. Step 4 tells us to place the wind velocity over the true airspeed. This is a step in which students commonly make an error of placing the grommet over the true airspeed. If you'll remember that the first 2 letters in grommet are also the first 2 letters in speed, you'll avoid this mistake. We'll very shortly be reading the ground speed under the grommet. We move the slide until the wind mark is over the true airspeed of 104 knots. Now we can read the ground speed under the grommet. Note that the numbers on either side of the grommet are 80 and 90. Since each intermediate line has a value of 2, we find the ground speed is 85 knots. When the wind mark is above the grommet, you know that a headwind exists. If the wind mark were below the grommet, you would be flying in tailwind conditions. Step 5 instructs us to read the wind correction angle between the center line and the wind velocity mark. The value we read is 10 degrees to the right of the center line, which is a plus wind correction angle. If the wind mark is to the left of the center line, the wind correction angle is left and is called a minus wind correction angle. While any student pilot can now add 10 degrees to 195 degrees true course to derive true heading, you will avoid gross errors by simply counting to the right of the true index 10 degrees to find the true heading of 205 degrees. On FAA private pilot examinations, the airplane speeds may be given in miles per hour. while winds aloft forecast speeds are always given in knots. So we must convert the wind speeds to miles per hour, as in this problem. Wind direction is from 110 degrees with speed forecast to be 19 knots. Your true course is 330 degrees and true airspeed is given in miles per hour, 122. What is the ground speed, the wind correction angle, and true heading? To convert the wind speed to miles per hour, we turn to the slide rule side of the computer and set 19 on scale B, the arrow marked naught for nautical miles on scale A. Under the arrow marked stat for statute miles, we read the answer 21.9, so we'll round out to 22 miles per hour. We now have all speed values matching, so we turn to the computer's built-in memory device and follow the steps. Step 1, place the wind direction under the true index, 110 degrees. Step 2 directs us to mark the wind velocity up from the grommet, so we count up from 100 to a value of 10, 20, 21, and place the wind mark. Step 3 is to rotate the disk to place the true course 330 degrees under the true index. As we rotate, keep an eye on the wind dot, noting its. Step 4 involves moving the slide and placing the wind mark over the true airspeed of 122 miles per hour. Be careful not to rotate the disk as you move the slide. Step 5 says we may now read the ground speed under the grommet. The ground speed is closest to 137. We have a tailwind. Step 6 now reminds us to read the wind correction angle between the center line and the wind velocity mark. Intermediate dark lines have a value of 5 degrees each, with each of the intermediate light lines a value of 1. We find the wind correction angle is 6 degrees, and because it is right of the center line, the correction is to the right, or a plus wind correction angle. We'll let the wind correction angle scale do our arithmetic for us and count 7 degrees to the right index, which is aligned with the true course. True heading is 336 degrees. We've now completed some of the calculations for dead reckoning navigation using the slide rule face and the wind face of the E6B computer. However, space-age electronics has made possible the development of a small, lightweight electronic navigation computer to replace the classic E6B manual computer. It's designed to solve all of the navigational problems which light airplane pilots are likely to encounter in the areas of in-flight planning and flight execution. The F-STARS keyboard is well organized and easy to follow, sort of like a textbook. The sequence of problems that occur in a typical flight are in the same sequence that appears on the computer's keyboard: altitude, airspeed, wind, time, speed, distance. After you turn it on, a small triangle located in the upper left side of the display tells you the battery condition. If the triangle appears dim or disappears completely, the batteries are weak and should be replaced. Some of the other features include the automatic shutdown capability. This helps to extend the battery life. A floating minus sign and decimal point. An error indication, which appears in the display if you make an input data error. An error correction capability. An automatic rounding feature that rounds off up to the nearest value in an 8-digit display, and a memory feature which can be used in all operations. Frequent reference will be made in this program to the different calculator modes. A mode is a specific key that performs a particular task. For example, at the top of the navigation mode is the altitude airspeed mode. Press this key and the computer is prepared to perform the task of computing either altitude or airspeed problems. Press this key, and the computer is ready to work wind problems. These are the same type of problems you would work on the wind face of the E6B. The electronic computer will solve these problems with greater accuracy than a manual computer. Time, speed, distance, and fuel consumption problems can all be solved by placing the computer in the TSD mode. The colored boundary lines are not here for decoration. They outline the data you will need to work problems in each of the three modes. Before we try a problem, let's turn on the computer. To do this, press the On Clear key. Now let's solve a true airspeed problem. You direct the computer to work a true airspeed problem by pressing the Altitude Airspeed Mode key. The letter A appears on the left of the display to let you know you are in the Altitude True Airspeed mode. You will tell the computer you are flying at an altitude of 7,500 feet pressure altitude. The outside air temperature is 20 degrees Celsius. The airspeed is 120 knots. What is the true airspeed of the airplane? First, turn on your calculator. Press the Altitude Airspeed key. Now enter 7,500 feet, pressure altitude, and press the pressure altitude key. Next, enter 20 degrees and press the T degrees Celsius key. Enter 120 knots and press the calibrated airspeed key. Now tell the computer to solve for true airspeed by pressing the Compute key, then press the True Airspeed key. Give your computer a few seconds to perform the calculations, and your display should read 139 knots. If you're finished with the computer, press the Off key. You save the batteries. But let's solve another true airspeed problem. Press the Clear key to prepare the computer for another problem. Note the upper left corner of the display. The letter A shows that the computer is still in the altitude airspeed mode, and the small triangle reminds you that the battery is okay. Now here's the problem. You are cruising at an altitude of 6,500 feet, and the outside air temperature is minus 10 degrees Celsius. The calibrated airspeed is 152 knots. What is the true airspeed of the airplane? First, enter 6,500 and press the pressure altitude key. Next, enter 10. To change this value to a minus value, press the plus or minus key. The minus sign appears in the display. Now press the temperature degrees Celsius key. Enter 152 and press the calibrated airspeed key. Ask the computer to solve for true airspeed by pressing first the Compute key and then the True Airspeed key. In a few seconds, the display will read 164 knots. One thing to remember, the Avstar will not accept true airspeed in place of calibrated airspeed. Be aware that some Federal Aviation Administration examination questions use true airspeed rather than calibrated airspeed, and you must convert it using your E6B. You'll use the electronic computer for navigation operations the most, so let's solve a density altitude problem. Your departure airport is Columbia, located in the Sierra Nevada mountains. The elevation is 2,112 feet. On a typical summer day, Columbia can warm up. For departure, the temperature is 95 degrees Fahrenheit, or 35 degrees Celsius. Begin this problem by pressing the On Clear key. Then place the computer in the Altitude True Airspeed mode by pressing this key. Check to see that the letter A is in the left-hand corner of the display. In this problem, the pressure altitude at Columbia is the same as the elevation, 2,112 feet. Enter this figure and press the pressure altitude key. The temperature is 35 degrees Celsius. Enter 35 and press the temperature in degrees Celsius key. Finally, tell the Avstar to solve the problem by pressing the Compute key and then the Density Altitude key. In a few seconds, the computer tells the correct answer is 4,838 feet. This is far more accurate than the answer you would calculate on the E6B. If you were plotting a course using the E6B computer, the next logical step in flight planning would be to solve wind problems. The Avstar works these problems quickly and accurately in the wind mode. Note again that the values necessary for the wind problem are enclosed in the red line. Stray outside that red fence in computing a wind problem and the Avstar will display error. Your wind problem is, at cruising altitude, the wind is forecast to be from 350 degrees with a wind speed of 28 knots. Your true course is 166 degrees and true airspeed is 112 miles per hour. What is the ground speed and what is the true heading? We need to convert either the wind speed or true airspeed so that the values are the same. The choice would depend on the value of the final answer. We want the answer in knots, so let's convert true airspeed to knots. Press on clear key, then enter 112, then press convert, then press statute to nautical, and the answer will appear quickly in the display, an answer more accurate than you can really use in flight planning, 97.325339, rounded out to 97 knots. To solve this problem, clear the computer and press the wind mode key. The B in the left display verifies the computer is in the wind mode. So enter a wind direction of 350 degrees, then press the wind direction key. Enter the wind speed of 28 knots and press the wind speed key. Then enter the true course of 16 degrees and press the course key. True airspeed of 97 knots is entered and the true airspeed key pressed. Now you can command the Avstar to compute for ground speed. And in a few seconds the answer will appear in the display, 125 knots. Next, you again press the compute key, and then the heading key, and the heading of 165 appears in the display. The other key in the navigation mode is the TSD key, time, speed, and distance. When you write out time in longhand, you place semicolons between the hours and minutes, between minutes and seconds. The Avstar writes in the semicolons for you when this key is pressed. But rather than displaying colons, the computer places dashes. For example, 2 hours, minutes, and 12 seconds would be displayed by pressing the time colon key between the numbers as 2 hours, 45 minutes, and 12 seconds. And enter as time by pressing the time key. The computer is now informed that the numbers entered represent time. Here are some practice entries, examples of various time values. Time is 13 minutes. Since the hours are 0, you need the dash or colon in front of the 13. You must first press the time colon key, then enter 13, and the display shows 0-13. If you wish to write 26 seconds, you must first enter 0 hours and minutes by pressing the time colon key, once for 0 hours and once again for 0 minutes. Then enter 26 seconds. A valuable feature of the Avstar is its capability to add and subtract time, exceedingly helpful in making logbook entries and in flight planning. Here's a sample problem. Your proposed departure time is 12:13. Your estimated time en route is 2 hours and 56 minutes. Find the estimated time of arrival. The Avstar simplifies the problem. Clear the computer, enter 12, then press time colon key. Now enter 13 minutes and press the arithmetic function key plus. Enter the estimated time en route by entering 2 hours, pressing the time colon key, and enter 56 minutes. Locate the arithmetic function for equals in the lower right and press that key for an estimated time of arrival of 15:09 or 3:09. Now try a subtraction problem. You need to arrive at your destination for an 11:15 business appointment. Your time en route is 3 hours and 32 minutes. What time would you have to leave to make your appointment? Clear the computer, enter 11, press time colon, Enter 15. Press the minus key. Enter 3 hours. Press time : and enter 32 minutes. Press the equal key to present an answer in the display. You find you must depart at 7:43 a.m. Time and distance problems make up most of the in-flight computations a pilot must solve, and a significant percentage of the pre-flight calculations. Be sure the Avstar is ready to go to work for you and that it is in the time, speed, distance mode. There is no letter indication that the Avstar is ready to work in this mode. Just as with navigation problems on the E6B computer, each basic problem consists of 2 knowns and 1 unknown. Let's solve one. Ground speed has been estimated at 112 knots on a cross-country flight of 272 nautical miles. How long will the flight require? The triangle on the display's upper left assures you the computer is on. Now place the Avstar in the time, speed, distance mode. Enter 112 knots and press the ground speed fuel per hour key. Enter 272. Then press the distance fuel key. Now tell the Avstar to compute the time. The readout of 2 hours, 25 minutes, 43 seconds is almost instantaneous. The computer will remain in the time, speed, distance mode unless you place it in another. So solve now for distance when time and speed are known. Ground speed is estimated to be 184 knots. Flight time is 6 hours, 32 minutes. How far can you fly under these circumstances? Clear the computer, enter 184 knots, press the ground speed key. Enter 6 hours, press time : key. Enter 32 minutes, press time key. Then press the compute key and ask the computer to give you the distance, 1,202.1 nautical miles. The knowns are a time of 12 minutes, a distance between 2 checkpoints of 34 miles. What has been the ground speed? First, clear the computer. Since the time is in minutes, you then press the time : key so the display shows 0 hours. Now you enter and press the time key. The display now shows 0 hours, 12 minutes, and 0 seconds. Enter 34 miles and press the distance fuel key. Command the Avstar to compute for ground speed, which is 170 miles per hour. Fuel consumption problems on the Avstar are comparable to time, speed, distance problems, just as they are on the E6B. You have refueled the skipper and find that you have consumed 12.7 gallons on a cross-country flight requiring 2 hours, 14 minutes. What is your fuel consumption? Clear the computer. Enter 12.7 gallons. Let the computer know these figures represent total fuel consumed. Enter 2 hours. Press the time : key. Enter 14 minutes. Tell the Avstar 2 hours and 14 minutes is the time of flight. Press the compute key, then the fuel per hour key. Your display should read 5.7 gallons per hour fuel consumption. Now you can leave that fuel consumption in the computer and ask it to tell you what is the aircraft endurance, or how long can the skipper fly at that consumption. The skipper has 29 gallons of usable fuel. First, you clear the computer, then enter 29. Tell the computer the number represents total fuel by pressing the distance fuel key. Now you ask the computer to give you the endurance by pressing the compute key and then the time key. Far more precise than the E6B could compute it, the time is 5 hours, 5 minutes, 59 seconds. The third fuel consumption problem involves knowing how long a flight will take. Then you find consumption in the skipper POH and compute the required total fuel for the flight. A flight has been estimated at 3 hours, 53 minutes, at an altitude of 5,500 feet, with a power setting of 2,400 RPM. The fuel consumption will be 5.5 gallons per hour. What is the total fuel required? Clear the computer, Still in the time, speed, and distance mode, you enter 3 hours. Press the time colon key. Note the display now shows 3-00. Now enter 53 minutes. Tell the computer 3:53 is the time, and the display verifies this fact. Enter 5.5. That is fuel per hour, so press the ground speed fuel per hour key. Command the Avstar to compute for the total fuel required, which is 21.4 gallons. You should legally determine how much reserve flight time will remain after you have consumed 21.4 gallons. So you clear the computer. Enter the usable fuel of 29, press the minus key. Enter the fuel consumed of 21.4 and press the equal key for the fuel remaining, 7.6 gallons. This value will remain in the Avstar's memory, but you must let the computer know it is total fuel, so press the fuel key. Enter 5.5 gallons per hour, which the skipper is consuming. Press the fuel per hour key. And then ask the computer for an answer in time of flight remaining, which is 1 hour, 22 minutes, 55 seconds. This exceeds the legal requirement for VFR day reserve by 52 minutes, 55 seconds. So welcome to the world of electronic navigation for light. You have completed all of the basic problems necessary for cross-country flight planning with computer-age speed and accuracy. Today's program will be the flight planning portion of a cross-country flight. The majority of your flying after the initial training hours will be cross-country, and this training is required to earn a private pilot certificate. As a learning experience, we will plan a scenic route, and one which will include as many aspects of navigation as possible which might be encountered in cross-country flying. Let's look at the planning of flight from San Carlos to Monterey, then to Los Banos, and return to San Carlos. It appears that a direct course from San Carlos will take us out over the Monterey Bay. A check of the airplane's glide performance in the pilot's operating handbook shows that an engine failure could mean an emergency landing on the water. Therefore, we'll alter the course to fly over Watsonville Airport, an excellent checkpoint. From there, we'll fly direct to Monterey Airport. From Monterey, we'll go direct to the Salinas VOR, then fly Victor 230 to the Panoche VOR to practice VOR navigation. Since Los Banos is almost on Victor 23 West, we can use that airway to fly to the Los Banos Airport. A landing at Los Banos will give experience at an uncontrolled airport. Then fly back to San Carlos. FAA regulations require that a pilot must obtain all available weather information for all points on a given flight. The next step, then, is to call the flight service station and ask for a weather briefing.
VFR?
It will help the briefer to know that you are a student pilot, and of course he needs to know what time of day you plan to depart, the route of flight, the estimated time en route, and the make and model of the airplane you will fly.
0600 Greenwich.
Based on the weather information, you make a decision to go or not to go on your flight. You should be aware that there will be times when the no-go decision is the only wise and safe one to make. On call-up, we get a report which we copy using abbreviations. This forecast does not indicate any weather problems unless we delay until late afternoon, when convective activity in the valley or fog in the coastal areas might be a problem. Since our plan is to depart at 8 o'clock in the morning, the ETA, estimated time of arrival, should be well before that afternoon period. With positive weather information and a go decision, the next step is very thorough pre-flight planning. We will need someplace to spread out the charts. You will also need your plotter, Avstar or manual computer, pen or pencil, pilot's operating handbook, the flight planner form or navigation log, and the airport facility directory. Now, get out your equipment and follow along as we go step by step to complete the flight log. First, we'll draw the course on a current San Francisco chart. Make sure the lines are drawn carefully from the center of each airport or VOR. On the first leg, from San Carlos to Watsonville, with the plotter still in place, make sure you are using the sectional measuring side of the plotter and make tick marks every 10 nautical miles along the course. And measure the distance. Then mark it on the chart. The first leg is 41 nautical miles. We shall later transfer this distance to the flight log. Following the same procedure, Watsonville to Monterey is 21 nautical miles. Monterey to the Salinas Vortac, 13 nautical miles. From Salinas on Victor 230 to the Panoche Vortac is 40 nautical miles. Panoche to Los Banos is 21 nautical miles. Return flight from Los Banos to San Carlos is 71 nautical miles. After laying out the course, we must check to make sure it does not take us through restricted airspace. Restricted area R2529 is on course inbound to Monterey, and R2511 is on course outbound. So we check the margin of the chart for floor and ceiling restrictions and the appropriate facility to contact for possible clearance through the airspace. Restricted area R2529 is Fort Ord West and is restricted up to 1,000 feet from 30 minutes before sunrise to 30 minutes after sunset. The controlling authority is Monterey Approach Control. R2511 is at Fort Ord and is restricted up to 5,000 feet continuously. The controlling authority is the same, Monterey Approach Control. Since both of these areas in the Monterey Tersa, the terminal radar service area, we will be in contact with air traffic control prior to entering both areas. There are no other restricted areas on this course. Our only other concern will be to stay below the San Francisco TCA on return to San Carlos. Now we need to put all of our information on the flight log so it will be compiled on one complete and readily available form. Using the three-letter codes for the airport facility directory, we enter SQL for San Carlos, the symbol for direct, and WVI for Watsonville. WVI to MRY for Monterey, Monterey to SNS for Salinas. Note the VOR frequency. Salinas to PXN for Panoche. Note that Victor Airway 230 is used and the Panoche frequency. Then to LSN for Los Banos. Enter the Airway Victor West and the Panoche VOR frequency. And finally, LSN to San Carlos. With the course outlined in this way, we need to start filling in the blanks on the flight log. True course is necessary to compute other aspects of the flight log, so let's start there. On a line of longitude near the center of the course line, Place the center hole of the plotter. Make sure the straight edge of the plotter is lined up with the course line. Using the outer scale for our course going from left to right, as the arrow indicates, we read 148 degrees at the point where the line of longitude crosses the protractor. Enter the true course on the flight log. For the Watsonville-Monterey leg, the course does not cross a line of latitude, so we must use a parallel or a line of latitude to measure the true course. Place the hole at the closest line of latitude and align the upper edge with the course line. Now use the lower portion of the inner scale to determine the true course for the direction of our flight. Read true course where the line of latitude crosses the inner scale. The true course is 188 degrees for the Watsonville-Monterey leg. Enter that in the flight log. The short leg of our flight, Monterey to Salinas, does not cross a line of longitude, so we need to move the plotter beyond the Salinas airport to locate one. We read the true course of 070 degrees and enter this on the flight log. The lines of longitude are not centered on the course between us and Panoche, but are near the beginning and the end of the leg, so either one is acceptable to use. The true course is 086 degrees. Enter it on the flight log. Panoche to Los Banos leg gives us another chance to use the inner scale of the protractor. Place the hole where the line of latitude crosses the course line. Make sure to align the straight edge with the course line. Now use the upper portion of the inner scale to determine the true course. Read true course where the line of latitude crosses the proper scale. True course is 348 degrees. Make your entry on the flight log. True course on the last leg from Los Banos to San Carlos is 202 degrees. We enter this figure. Now we enter the distance figures from the chart in the proper column. Next, we should look at the terrain on the route and determine the safe altitude for the flight. The highest terrain or obstacle on the first leg is a 4,079-foot tower located in the Santa Cruz mountain range. We must determine magnetic course to apply the hemispherical rule and determine proper altitude. Using true course of 148 degrees minus 16 degrees east variation, we have 132 degrees magnetic course. The proper altitude will be 7,500 feet. Always plan to fly at least 2,000 feet above obstacles, either directly on or along your route of flight if possible. This is considered a good operating practice, which will provide a margin of safety in the event of an emergency. Enter cruising altitude in column 1, 7,500 feet. There are no terrain restrictions to altitude on the Watsonville-Monterey leg, but at any point where magnetic course changes, we must verify if an altitude change is required by regulation. True course equals 188 degrees minus 16 degrees easterly variation gives a magnetic course of 172 degrees. This magnetic course dictates no cruising altitude change, but we need to start a descent in preparation for our approach into Monterey. After departure from Monterey, we will be under ATC control because of the TIRSA, but we do our own planning for altitude to fly once control is terminated. 5,500 feet altitude can be used on this leg and will be adequate to cross the 3,058-foot obstruction and the 2,909-foot peak en route to Panoche. Enter 5,500 feet for both legs. We make a course change from 070 degrees magnetic inbound to Panoche to 332 degrees magnetic outbound. This dictates a change of altitude en route to Los Banos. With no obstructions and a short leg, descending to 4,500 feet is our choice. Homeward bound to San Carlos, the mountains rise up to a peak of 4,380 feet at Mount Hamilton, where the Lick Observatory perches on top. This leg will be flown at 6,500 feet to give safe and proper clearance. The next column is a listing of indicated airspeed and true airspeed for the flight. We must refer to the cruise performance chart in the pilot's operating handbook to determine these figures. First, locate 7,500 feet, which is our altitude for the first two legs. Select 2,400 RPM to conserve fuel and read indicated airspeed of 82 knots and a true airspeed of 91 knots. 5,500 feet is the altitude for the next two legs. Enter the numbers 85 for indicated airspeed and 92 for true airspeed. At 4,500 feet on leg 5, indicated airspeed will be 87 knots and true airspeed will be 93 knots. And the homebound leg at 6,500 feet with an indicated airspeed of 84 knots and a true airspeed of 92 knots. Next, referring to the weather information received on our call to the flight service station, we'll check the winds aloft forecast for the route. We may either use altitudes close to ours or interpolate when there is a great difference. These are the forecast winds as we jotted them down on our briefing sheet. 300 degrees at 11 knots for leg 1 with temperature of plus 4 degrees. 300 degrees at 11 knots for leg 2 with temperature plus 4 degrees. 290 degrees at 10 knots for leg 3 and plus 5 degree temperature. 290 degrees at 12 knots with temperature plus 5 degrees. Leg 5 is wind from 285 degrees at 11 knots and temperature plus 7 degrees. The final leg is wind from 290 degrees at 12 knots with temperature plus 5 degrees. All of the information listed on the flight log, we can now do some mathematical computation to fill in the rest of the blanks. We note the next column is wind correction angle and true heading. The Avstar will simplify the computations. We will also work this same wind triangle problem on the E6B style computer for those without Avstars. Press the On button on the Avstar, then the Wind mode. Note the B on the display to assure the correct mode. Then enter 300 degrees, wind direction for our first leg, and press the Wind Direction key. Enter 11 and press Wind Speed. 148 and press Course. 91 and press True Airspeed. All necessary entries are now in the computer. Press the Compute button, then Heading button to determine the true heading of 151 degrees. Press the Compute button again, then Ground Speed to find a ground speed of 101 knots. Enter these figures on the log. This method does not give a wind correction angle, but gives the true heading directly. Now let's work the same problem on the E6B. Set the wind direction 300 degrees under the true index. Mark the wind velocity 11 knots counting up from the grommet. Next, set the true course 148 degrees under the true index. And then move the slide to place the wind dot you made under the true airspeed of 91 knots. Wind correction angle is now read from the center line and is 3 degrees right. A right wind correction angle is added, so true heading is 151 degrees. Ground speed is read under the grommet and is 101 knots. Once computed, we enter true heading and ground speed for each leg of the flight. We have a heading for leg 2 of 194 degrees and a ground speed of 95 knots. For leg 3, the heading is 066 and a ground speed of 99 knots. On leg 4, the heading is 083 degrees and a ground speed is 103 knots. For leg 5, the true heading is 342 degrees and ground speed 87 knots. Stretch figures are a true heading of 292 degrees and ground speed of 80 knots. The next column in the flight log is for amount of variation and the determination of magnetic heading. We must look to the sectional chart for the dashed magenta isogonic line and the degrees of variation. Remember, variation is the difference from true north to magnetic north and is needed because we navigate by use of the magnetic compass. In the area between San Carlos and Monterey, we see an isogonic line of variation almost midway through the course, which continues across to the midpoint of the final leg. The number is 16 degrees east, and this is what we will enter in the flight log for all legs. The letter E indicates that the 16 degrees will be subtracted from the true heading. Remember, east is least, west. On some flights, the variation may change for some portion of the trip, and you should include these changes in your flight log. Subtracting 16 degrees from the heading for each leg, the magnetic headings are 135, 178, 050, 067, 326, and 276. The deviation and compass heading column are next. Deviation is the result of electronic interference from radios and magnetic disturbances in the aircraft, and this is added or subtracted from the magnetic heading to determine compass heading. Each aircraft has its own compass card showing deviation for that particular airplane only. Our skipper has 0 degrees deviation. Consequently, the compass heading will be the same as the magnetic heading, so we can transfer those numbers to the compass heading column. Now we can compute the estimated time en route and the estimated time of arrival for each leg of the flight. Using the Avstar, press the TSD button to activate the time, speed, distance mode. We have previously computed distance and ground speed, and we feed these into the computer to find the estimated time en route. Enter the first leg ground speed of 101 knots. Enter the distance, 41 nautical miles. Ask the computer to compute for time, and the answer is 24 minutes, 21 seconds, which we'll round off to 24 minutes and enter on the flight log. Following the same procedures for each leg, our flight log entries would be 13, 08, 23, 14, and 53. Simple mathematics will be used to compute our estimated time of arrival, the ETA. If departure is at 0800 and the first leg ETE is 24 minutes, our ETA will be 8:24. The remaining ETAs will be calculated in flight. Next, we need to determine the amount of fuel needed for this flight. Checking again on the cruise performance chart, we note that fuel consumption at 7,500 feet is 5.3 gallons per hour. At 5,500 feet, 5.5 gallons per hour. At 4,500 feet, 5.6 gallons per hour, and at 6,500 feet, fuel consumption is 5.4 gallons per hour. Let's average for a rate of 5.5 gallons per hour for the flight. The procedure for computing the fuel consumed is as follows. Press the time, speed, distance button to activate the probe. Next, press the T button to display 0 hours. Then enter 24 minutes and press the time button. Make sure not to confuse the T button with the time button. The computations will not work if they are switched. Next, enter 5.5 and press the fuel per hour button. Press the compute button and the distance fuel button. Now check the fuel consumed on the display. On this leg, it is 2.2 gallons. You would compute for each leg in the same manner. For the sake of time, we'll just write in our answers on the log. You should also take into account time to climb and fuel to climb when flight planning. For this trip, both factors would not make a significant difference. Now we need to total the amount of fuel to be used on the flight. This is simply the sum of the amount for each leg, and we have a total of 12.7 gallons necessary for the flight. The total usable fuel carried by the skipper is 29 gallons. We complete the final column of the flight log by subtracting fuel used on each leg from the previous total. 29 minus 2.2 leaves 26.8 gallons remaining. Then 25.6, 24.9, 22.7, 21.4, and 16.5 gallons remaining. This more than satisfies the 30-minute reserve required for VFR flight. The other areas to complete on the flight log include frequencies to be used en route. Most frequencies can be found on the chart, but we need to use the airport facility directory for complete information. Here is San Carlos information. We'll list it in the first column. ATIS is 125.9. There's no clearance delivery at San Carlos, but ground control is 121.6. Tower is 119.0. Bay departure control is 135.65. Bay approach control is 133.95. For the flight service station, only a phone number is given in this listing, so we'll check the chart to find 122.5 listed above the box with Oakland Radio's information. Unicom is 122.95, a standard Unicom frequency for tower-controlled airports. While we have the page open to San Carlos, let's check the field elevation listed on the second line and enter that in the flight log. In the next column, we will list Monterey information, so we turn to the Monterey of the airport facility directory. ATIS is 119.25. There is no clearance delivery available. Ground control is 121.9. Tower, 118.4. Approach and departure control indicates different frequencies for different sectors. Use 120.8 for our departure heading of 050. Approach control frequency for the inbound heading of 178 degrees is 127.15. Once again, we refer to the chart for the correct flight service station frequency. Salinas frequency is 122.6, and Unicom frequency at Monterey is 122.5. We'll also enter the Monterey Airport elevation of 244 feet. Los Banos Airport is uncontrolled, and we can get the necessary information from the sectional chart. Elevation is 119 feet. Unicom is 122.8. And the nearest flight service station to contact is Fresno, as indicated below the box at Merced VOR and at Penoche Vortac, the two stations closest to Los Banos. The frequency is not listed, so we know to use the standard frequency of 122.2. The only other information we can complete at this point comes under the very important reminder in the lower right-hand corner, remember to close your flight plan. Since this is a round-robin flight, we will close with the same flight service station we opened, Oakland, on frequency 120.5. The phone number is given in the airport facility directory, so let's enter the information to have it handy in case we cannot contact the facility from the air. The other aspects of the flight log will be completed as the flight progresses. The ATIS advisories will be copied at San Carlos prior to taxi and contacting ground control, and the same at Monterey. Now our flight log is complete. In our next program, we'll fill out an FAA-approved flight plan, perform our pre-flight inspection, then depart San Carlos at approximately 1600 Zulu. At that time, we'll see how important careful flight planning is to cross-country flying. Hello. Today's the big day for the cross-country flight we so carefully planned on our last program. I've double-checked the weather forecast, and we have good VFR flight conditions along our route. I also had the skipper refueled prior to performing the pre-flight inspection. There's still one item to complete on our flight log, so we'll enter a 30-minute stopover at Monterey and Los Banos in the remarks section. Now, a check of our navigational and personal equipment. Chart, plotter, computer, pencils, flight log, flight plan copy, logbook with instructor endorsement for the flight, student pilot and medical certificate also properly endorsed, radio operator's license, and sunglasses. All that's left now is to file our flight plan using the FAA format. These forms are available at flight service stations and most fixed-base operations. You can see it is used for VFR, IFR, and DVFR plans. The DVFR is used when crossing the defense area of the United States borders. This flight will be VFR, so check the proper box. Aircraft identification is next. The skipper numbers are N 37259er. Block 3 asks for aircraft type. The skipper is designated as a BE-77. Special equipment on board is the transponder, so use the slash as indicated and the code for the transponder with encoding altimeter U. Airspeed was computed as 92 knots. Departure point is San Carlos, SQL. Proposed departure is requested in Zulu time. Our takeoff is scheduled at 0800 Pacific Standard Time, so we must add 8 hours to convert to Zulu time, 1600 hours. The initial flight planning altitude is 7,500. Route of flight is requested next. We'll use the 3-letter codes from the airport facility directory and the symbol for direct flight, as we did on our flight log. San Carlos, direct to Watsonville, then direct Monterey, direct Salinas, then on Victor 230 to Panoche, direct to Los Banos, direct to San Carlos. Our destination airport is San Carlos, at the city of San Carlos. The total estimated time for our cross-country flight is next. We'll total the ETEs from our flight log and add the stopover times noted in the remarks section. 2 hours, 16 minutes, plus 30 minutes at each stop, totals 3 hours, 16 minutes. In the remarks section, we'll note the 30-minute stopovers at Monterey and at Los Banos. The next request is for fuel on board. Remember, the skipper carries 29 usable gallons. With fuel consumption at 5.5 gallons per hour, we could stay airborne for 4 hours, 32 minutes. An alternate is not required for this VFR flight. Mark that column not applicable. And then your name, address, and phone number must be filled in. Number of persons on board, 1 for this trip. Aircraft color is white and blue, and the facility where we close the flight plan is Oakland Flight Service Station. Now, with a phone call to Oakland Flight Service Station, we can file our flight plan, giving the information in the order that it's listed on our form. Now it's time to get going. We'll tune in San Carlos ATIS, listed as 125.9 on our flight log.
San Carlos information, Alpha time 1530 Greenwich, temperature 63, wind 300 at 8, altimeter 299.7.
We'll tune in ground control on 121.6. San Carlos ground, skipper 37259er at area November with Alpha. Request taxi for takeoff.
Skipper 259er, San Carlos ground, taxi to runway 30 and hold. Contact tower at 1190.
We have clearance to taxi to the run-up area, where we will perform our pre-takeoff checklist before requesting clearance for takeoff. San Carlos Tower, skipper 37259er, ready for takeoff. Request right downwind departure.
Skipper 259er, right downwind approved, cleared for takeoff.
Looking for other traffic, we turn on to our course toward Watsonville. Stanford University is our first pilotage checkpoint. We're steady now on our heading of 135 degrees. And we must remember to activate our flight plan with Oakland Flight Service on 122.5. Oakland Radio, skipper 37259er, listening 122.5, over.
Skipper 259er, this is Oakland Radio. Go ahead.
Skipper 259er, VFR San Carlos, round robin to Monterey and Los Banos. Please activate my flight plan. Departed San Carlos at 00.
Skipper 259er, roger. Your flight plan activated. San Jose altimeter 299.8.
Skipper 259er, altimeter 299.8. Thank you. The highway below we know is Highway 280, and this symbol for mines and quarries marks another good pilotage checkpoint. It represents the cement plant just to the right of our course. We level out at our cruising altitude of 7,500 feet and perform the cruise checklist. In a minute we will cross another freeway, and the lake there with the dam, that's Lexington Reservoir. So we know we're on course, verified by pilotage navigation, our identification of landmarks. In a few minutes, we'll be at our first checkpoint, Watsonville Airport. There it is on our left. We'll watch for traffic and monitor 122.8 Unicom frequency for this uncontrolled airport. We note the time over Watsonville, 8:24. So we're on schedule. For the second leg of our flight to Monterey, we turn to our outbound heading of 178 degrees. Our ATA at Watsonville was 8:24, with a 24-minute ATE. Our ETE for the next leg is 13 minutes, so our ETA at Monterey is 8:37. Pilotage navigation on this leg is as simple as following the shoreline of the Pacific Ocean. But the airspace is more complicated than the navigation. Monterey has a Terminal Radar Service Area, abbreviated TIRSA, and we'll fly over a restricted area R2529. We know from our flight planning that the area is restricted up to 1,000 feet MSL, but we'll fly well above that. We'll listen to the Automatic Terminal Information Service, ATIS, before we contact Monterey Approach Control for TIRSA service.
68, wind 310 at 9, altimeter 299er2, Stratus West.
It is a requirement of Federal Aviation regulations that we set the altimeter to that of the nearest reporting station. Then we are assured that all aircraft flying in the Monterey traffic pattern are flying by reference to the same setting. Stage 3 is available from Monterey Approach Control and provides advisories of other aircraft flying in the area. Checking our flight log for Approach Control, we tune to 127.15. Monterey Approach Control, Skipper 37259er, over.
Skipper 259er, Monterey Approach Control, go ahead.
Skipper 259er, Moss Landing, passing through 500, squawking 1200 with Bravo. Request Stage 3 service for landing Monterey, over.
Skipper 259er, roger. Squawk 0367 and ident.
259er, 0367.
Skipper 259er, radar contact. Maintain VFR conditions and descend to 1,500 for right traffic, runway 28, over.
Skipper 259er, leaving 5,000 for 1,500.
Roger, Skipper 259er. Traffic, 2 o'clock, 3 miles southbound, a Republic DC-9 at 2,000.
259er, I have the traffic.
Skipper 259er, radar service terminated. Contact Monterey Tower 118.4. Report the freeway, over.
Skipper 259er, 118.4. This is one of the most picturesque airports in the West, and for a relatively small one, it's very busy. Monterey Tower, Skipper 259er over the freeway, turning downwind.
Skipper 37259er, Monterey Tower. Number 2, follow the Republic DC-9 on a 10-mile final for runway 28.
Skipper 259er, number 2. Since we're following the DC-9, we're aware of the dangers of wake turbulence caused by wingtip vortices. We also know that on approach and landing, if we stay above the airliner's approach path and land beyond the point of touchdown, we'll be above the wake turbulence and out of danger. So we'll plan our approach with this safety margin in mind.
Skipper 259er and runway 28, caution wake turbulence.
259er, thank you. We've completed our pre-landing checklist, so we're ready and cleared to land. By using the visual approach slope indicator, we'll stay above the glide path of the DC-9 and should avoid the wake turbulence.
Skipper 259er, contact ground control 121.9er.
Monterey ground, Skipper 37259er, clear of 28, taxi to transient parking.
Skipper 259er, Monterey ground, taxi to transient parking.
We note the time, 8:37. Good, precisely as planned. So that completes the first leg of our cross-country flight. Since we'll be leaving the skipper unattended for a time, it is necessary that we secure the airplane with tie-downs or chocks before going in search of the pilot's lounge. Here we bring our flight log up to date. Our time of touchdown was 8:37. Our actual time en route was 13 minutes, so our planning was accurate. We've allowed time for a cup of coffee and perhaps a snack while we review our flight planning en route to Los Banos. We recall that our route takes us through another restricted area, R2511. However, it is possible to obtain clearance through the airspace from Monterey approach control. Let's check the flight log for our heading outbound from Monterey, 050 degrees, and our altitude to the Salinas VOR, 5,500 feet. It's now 8:53, and since we've allowed just 30 minutes on the ground here, we should get moving. Even though we did pre-flight the skipper at San Carlos, we go through another complete pre-flight before departing Monterey. Always pre-flight your airplane before every departure. After listening to ATIS, we're ready to contact ground control for clearance through the Monterey Tursa. Monterey ground, skipper 37259er, transient ramp, request stage 3 service to Salinas, ready to taxi. After receiving our taxi clearance, we proceed to taxi to the active runway. Remember, a clearance to the active runway includes permission to cross all other runways. While taxiing, ground control may call with additional instructions or an amended clearance. This is also a good time to double-check that you have set the correct transponder code. After arriving at the run-up area and completing our run-up, we are ready to call Monterey Tower for takeoff clearance. Monterey Tower, skipper 37259er, ready for departure, runway 28. After receiving our clearance for takeoff, we are ready to begin the next leg of our trip to Los Banos and then back to San Carlos. Remember, shortly after takeoff, we can expect the tower to give us a handoff to Monterey Departure Control for our Stage 3 service out of the Tursa.
259er, contact Monterey Departure 120.8. Good day.
Skipper 259er, 120.8. Good day. Monterey departure, skipper 37259er, out of 1,500 for 5,500.
Skipper 259, Monterey departure, radar contact. Transit approved, Romeo 2511, below 5,000 via direct Salinas VOR.
Good. We've received clearance through the restricted area R2511.
Skipper 259, radar service terminated, squawk VFR. Good day.
The phrase radar service terminated means that departure control will no longer provide advisories of other traffic. Squawk VFR means that we must change our transponder code from the departure code of 0361 to the VFR 1200. Our time of takeoff from Monterey was 9:07, and our ETE to Salinas is 8 minutes, so our ETA is 915. Since we received radar vectors on departure from Monterey, we cannot use our planned heading 050 to Salinas. So we tune Salinas VOR and identify it.
Transcribed aviation weather broadcast, weather observed at 2 p.m. unless otherwise stated.
Then we turn the OBS to center the needle and turn the airplane to the heading indicated, 018 degrees. We'll fly the indicated course and be alert for deflections in the course deviation indicator. We'll fly toward the needle to bring it back to center should it deflect right or left. But we'll also verify our position by pilotage. Eccles Sugar Plant is a prominent landmark slightly right of our course, 3 miles southwest of Salinas. We've reached our cruising altitude of 5,500 feet. We're coming up on Salinas VOR now, as indicated by the wide deflection of the CDI. We'll hold our heading until we cross the station. Now the flag tells us we're over Salinas. a fact we can easily verify by our view of the airport with the VOR located on the field. We check the time, 0915. We note station passage at 9:15. Our ATE is 8 minutes. Our ETE to Panoche is 24 minutes, so our ETA is 9:39. Now we'll turn on to our course to Panoche VOR. We'll establish ourselves on Victor Airway 230 with a heading of 0 degrees and make course corrections as required. And now we can make a position report to Salinas Flight Service. Salinas Radio, Skipper 37259er, listening on 122.6, over.
Skipper 259er, Salinas Radio, go ahead.
Skipper 259er on VFR round-robin flight plan, San Carlos, Monterey, Los Banos, San Carlos, over Salinas VOR at 5,500, over.
Skipper 259er, roger your position, Salinas altimeter 29er, 9er7.
Skipper 259er, 29er 9er7.
We continue to navigate using Salinas VOR, but checking our position by pilotage. Across the Gavilan Mountain Range and over the San Benito River. We're midway now between Salinas and Panoche, so we'll navigate using Panoche VOR for better reception and accuracy. Okay, that's it. Now it's necessary to reset the OBS to the published inbound magnetic heading of 070 degrees. And the view from this altitude is truly breathtaking. We're approaching Panoche VOR now. In fact, we can even see it perched atop a barren hill. It's in mighty desolate country, even as close as we are to populated areas. The needles swing and the flags flip from to off to from verifies station passage. Not bad, 1 minute earlier than our ETA of 0939. We'll ATA at Panoche of 9:38, then our ATE of 23 minutes, and compute our ground speed. Press the time speed distance button, press T, then 23 minutes, and the time button. Enter 40 nautical miles and then distance button. Push the compute button, then ground speed, 104 knots. We'll use this to compute our ETA at Los Banos. Then enter 21 nautical miles, our distance to Panoche. Press the distance button, compute button, then time for our ETE of 12 minutes to Los Banos. Our ETA will be 9:50. We reset the OBS to our outbound course of 326 degrees and turn to that heading. Now it's time to start our new altitude of 4,500 feet. 500 feet per minute will be a good rate of descent. The magenta color of the Los Banos airport symbol indicates the airport is uncontrolled, but airport advisories are available on the Unicom frequency 122.8. Los Banos Unicom, Skipper 37259er, over.
Skipper 259er, Los Banos Unicom, go ahead.
259er, 10 south for landing, request airport traffic advisories.
Skipper 259er, Los Banos wind favoring 32, altimeter 29er86.
Skipper 259er, understand runway 32, altimeter 29er86. Thank you. From the airport facility directory, we know that the traffic pattern is standard for runway 32. Left-hand turns. So we orient for a 45-degree entry to a left downwind leg. Los Banos Unicom, Skipper 259er, turning left downwind, runway 32. We broadcast in the blind at uncontrolled airports. That is, we announce our position in the pattern so that other airplanes know our position. We'll take a few minutes for refreshment while we make our flight log entries and double-check the weather for our flight back home. Then, after a thorough pre-flight check, it's takeoff time on the last leg of the flight. We establish that we are on course for pilotage navigation, using the distinguished peak, Mount Hamilton, with its observatory perched on top. The mountain guards the entrance to the Santa Clara Valley and to the San Francisco Terminal Control Area, which is a factor on our choice of altitudes on descent to San Carlos. We'll start descent now so as to be below 6,000 feet as we pass San Jose Airport. We'll continue descent below 4,000 before we pass abeam the giant hangars of Moffett Field. Now we request clearance through the Palo Alto Airport traffic area. Here, the San Francisco TCA restricts us to an altitude of 2,500 feet. We're right on the course we set from Los Banos, 276 degrees. And we're right on time, 5 minutes from San Carlos and 5 minutes from our ETA of 11:14. But there's still a lot of work to do. We'll tune in San Carlos ATIS on 125. And scan for traffic. We're accustomed to seeing airliners to our right inbound to San Francisco International Airport, but they're not a factor in our approach to San Carlos. We're ready to contact San Carlos Tower on 119.0. San Carlos Tower, skipper 37259er, 7 southeast for landing with Charlie.
Skipper 37259er, San Carlos Tower. Make a straight-in approach. Report a 2-mile final at Kaiser Hospital at or above 1,200.
Following the tower's directions and using the runway's VASI system, we make our landing at San Carlos at 11:14, exactly as planned. Ground control will take us from here. Well, we still have to place a call to Oakland Flight Service Station to close our flight plan, tie down the skipper, and put in a refueling order. We'll also complete our flight log with information gathered along each leg of the flight. We followed our flight plan with precision, and the rewards were a safe, efficient, and pleasurable flight. An excellent example of why careful flight planning is essential to the execution of a good flight.